Yeah, let's start with the last chapters of chapter 9 of this lecture. 2 weeks left, some supplements, some supplement information to the PFC and to the my version of the deadbeat controller, which should deliver some ideas what we can do more if we have an intelligent computer system available. Yeah. First is the point 9.8.1. Some words to disturbances and disturbance measurement. Disturbance measurement. Sometimes it is useful to have information about disturbances of your system. In some cases, the systems are expanded with additional disturbance sensors. I want to show you a page of control system 1 where we have optimized a system with that what we call disturbance feed-forward. Yeah, that is the method on page 51 of the workbook, control system 1, where we have a disturbance here, Z2, and if the controller of the closed loop system is not fast enough, not good enough to compensate this disturbance, so that this disturbance has here too large influence, then a good idea to improve the system is measure the disturbance, look for a good compensation filter, and add this disturbance compensation here to the actuator. Now this is the actuator of your normal closed loop system. Here add the signal to the output of the controller, and then this is called disturbance feed-forward. But hardware additional necessity is you need a disturbance sensor, and sometimes the disturbance cannot be measured, or it is expensive to measure the disturbance. Now I show you a method where you don't need an additional hardware sensor. You can do this also with intelligent software. Okay, how can we do this? There is a picture in the lecture I have copied out of the book of Mr. Richalet. The idea he presented there was charming, and let's look for this picture. Picture is gone. Okay, I have to look for the picture here. Control copy, the control V. This is the signal block diagram of a measurement of the disturbance. Here you see this is the perturbation, he called this perturbation, perturbation, another word for disturbance. Yeah? Disturbance, I'm not sure if the disturbance or perturbation is a better expression. So there is an external unknown influence to your system. This is the original process. Yeah, note, this is the process. Maybe there is another disturbance at the end of the process, but this of course can be shifted to the input of the disturbance. We measure this signal independently of this disturbance has an influence at the end, in the middle, or in the beginning of the process. We only want to have this signal without a hardware sensor. Okay, then note here, this is the normal controller software, PFC or DB or PI or any controller. This is the set point, the desired value, the measured value, and this is the MV is that name what Mr. Richalet called it, the French, manipulated variable. Manipulated variable. MV is the output of the controller. Output controller in our writing the y value, y of k or so. Manipulated variable. The letters come from that is just controller output. Okay, you see the controller output now goes to the summing point where the unknown disturbance is added, and this influences the process, leads to a controlled output. This controlled output is with the feedback going into the controller. So this is the original loop which is disturbed. You have a set point here, disturbance there, and okay, what we can do more is that what you see here in the mathematical second section of this picture. There you need a model, and we have a model still in our model-based system, model-based controller or predictive controllers. There is a model available, so we have this model of the process. Here you have a second model running in the process, in this box. This is the best identified model what you can need, but if you have model-based controllers, you need this model. So this is available also as software, as coefficients A's and B's. Okay, then you copy this controller. You have a second control loop. You now build a mathematical simulated second closed loop system with a process which is modeled, and here the same controller should run then there. So if this is a deadbeat by, this should be a deadbeat by. If this is a PFC, this is a PFC. If this is a PI, this is a PI. So you copy just the algorithm of your controller a second time and run this loop with whatever kind of set point, not the same set point. Then this won't help. You need the controlled output as a new set point here. So normally this and that values are the same, but the trick is you use now this set point as a set point, this output, this controlled value output as a set point for your second loop. So that will lead to the to the next step. We assume that this controller is following this value. So after some steps of if there is a step here, there will be a step response there, and this step response comes as an input. So this is a step response of the step response. So this maybe has some delay, but finally this value and that value are equal. If this is a good controller, we assume that it's a PFC or any other good controller, then this set point will be the same than this set point. So our output of the process is equal to this value. We assume in the first thinking that B is 0, or we shifted this value and add this to this disturbance. We only assume that there is an input. Okay, if this value and that value now are equal, you see we have the process, the real process output, and the output of the modeled output, which are equal. Then we know the input here is equal to our second manipulated variable, and here we know this input and this input should be the same. So the difference between this controller output and this controller output, the difference must be the signal. So this I just calculate the difference of the both controller outputs and get a value for my disturbance. That is a very nice trick to avoid a hardware disturbance sensor. And what you do with this signal is a second question. You can make a disturbance feed-forward, or that what I will show you in my last chapter next week is I use this information to force my control error of my controller to 0. So I measure the disturbance, and then I need this and use this signal to compensate this disturbance completely in this loop. Wait for this second step of a very good trick to improve your controller. So if you want to have this disturbance, that's a good way. So for example, if this is a room temperature control system, then use this trick to measure the main important disturbance you have in your room control system, which is the ambient temperature from outside. Normally, many room temperature control systems have a sensor, a hardware sensor at the outside of your house, of your wall, to measure the outside temperature. With this trick, this is not necessary, because here this temperature controller and this model temperature controller gives automatically exactly this result without a hardware sensor. Mr. Richeli is describing another application for this. In the chemical industry, they have so-called batch processes. Batch processes means they have a big tank, so hundreds of tons of material which is mixed and filled in a big big bottle, we can say, and then this is heated, and then internally in the box there are chemical processes which also produce heat. This then disturbs your process, because then this heat comes additionally to your heater and disturbs your temperature control system. With this system, they measure the heat which is internally created by chemical processes, and then can be used to optimize the temperature controller of your batch process. Now, this is a good way. There is no additional sensor available in your tank. You cannot fill this with temperature sensors. The temperature sensor will melt, or the cable will melt, because this plays with temperatures near 1000 degrees or so. So this trick is very helpful in many processes, so keep this trick in mind if you have any similar problems, to say, okay, I can remember there was a trick, let's play with this trick. So in other words, again, if I use this signal as a desired value for my second loop, then I know B0, I know that the output of my real process is equal to the output of my model process. So I know the input here is equal to the input there. So I have here a signal which is a good measurement for the unknown input of your process. The input of the process is unknown because the disturbance is unknown. We know MV1, but this is unknown, so this is also unknown. But with this trick, this value is equal to this value, and so we have a possibility in the summing point. If this is known and this is known, we can recalculate the perturbation or the disturbance. So I think this should be clear, and I want to show you this in my simulator, where I use this trick to show you the measurement of the disturbance in some examples. So I open my simulator, WinDF C#. This is a fresh started simulator, WinDF C#. And first I show you the system with our well-known 2PT1 system. I load just the FZ file of our 2PT1 system, which we have used as a simulation in previous steps. So K is 0.4, T1 is 100 millisecond, T2 is 20 millisecond. We want to sample with 10 millisecond. So this, and I think, yeah, let's start with ideal algorithm. Okay, we make a controller design to have good running controllers, ideal version, FC loads the same process. I make a controller design in ideal version, send all controllers to my box, and click on this point. This is a good point to send the A's and B's to my PFC box. Sometimes this can also help to have just less typing in. So I close this, open my advanced adaptive box. So I have here 10 millisecond is okay. Ideal algorithm is switched. Unit step function, is that what we want to see here? And to see also PFCs, we can open this radio button with advanced view. So I can now shift this up because we want to see curves here in this region. I just show you how to display this disturbance measurement in our PFC parameter box. There is a button. Ja, wie komme ich da jetzt ran? There is a button. This window is rather large, so I have to open it. A button where I can use my measurement. In normal signals I can measure are X, the controlled output, the most interesting signal. Then W is the desired value. Sometimes this is interesting, how large is the desired value, and this is the controller output. If you click this, you see in the second curve the controller output. I have now, don't want to have more buttons here. So what I have done is I can now change the signal for the controller output to either I want to see the second prediction of my deadbeat by, or here you see this is a disturbance. I measure with this principle. So if I click this checkbox and this checkbox with this radio button, then the signal, which is presented here with the name XR, contains the measured disturbance. Okay, let's play now with a controller. Say I play with the PFC deadbeat, with the PFC of Mr. Richalet. Here the process parameters are still copied. I just take H is 2 and 80 milliseconds, the default values, why not? And now I run the loop and you will see no disturbance, because there is no disturbance. I of course should now switch to a disturbance response, because then I know the disturbance is a step function. Disturbance is a step function. And now look what happens if I go into this and measure the disturbance step response. I see one signal, that is a disturbance step response of my controller, but I see no disturbance here. Okay, there is something wrong. Schade eigentlich. Okay, I have to check. Yeah, I'm very unhappy because we have seen now an error in my software. Okay, if I measured the disturbance first with my deadbeat by, independent of all these parameters, then you will see that we will see two curves, and one curve is here, the small, the disturbance, response. It's very small, but here the red curve is now the measurement of the disturbance, of the perturbation with this principle. And you see, after some steps, we have 10 milliseconds. So here, this is the situation after 6 to 7 steps. We have a constant, clear signal of a signal with the amplitude 1, because we have amplitude 1 at my disturbance input. So after a transition, we see a disturbance signal which is exactly 1. If I have the PFC, if I no click on this, then this works. The first time I click on this disturbance measurement doesn't work. I have to look into the code. There must be a small, simple error, but with this version you can avoid this. First start with my controller and then go to this point, and then you see the disturbance response with the PFC, measured with the PFC controller. I delete all curves, start measurement, and you see here the disturbance response of the PFC, the real PFC controller, and here the red signal is really the measured disturbance, and you see after one step the disturbance signal is exactly 1. So if you have the same controller in the second loop and in the first loop, you see the disturbance behavior looks disturbance behavior, not the disturbance signal, looks very good. This works also if you use other controllers. P controller, let's check. If I do this, you see it's the same. Let's check if I see a similar situation. Yeah, the black curve here you can see, because the black curve is identical to the if I make the curve a little bit thicker, then you can see the black curve is just exactly this value. So this is proof that the disturbance measurement is really working, and I get here a software signal for my input disturbance, and this will be used then in the next week chapter, I think 913, to improve my deadbeat version to come to a better disturbance behavior. Okay, so far this disturbance measurement. So in the next video I then add the PFC with for IT1 processes.